Hello everyone, welcome to Physics online classes for class 12 students. Let us continue chapter 6 Electromagnetic Induction. Today we are going to study about self-induction. Yes, we completed up to eddy currents. See here, in this chapter we studied magnetic flux, Faraday's 3 experiments, Faraday's laws of electromagnetic induction, and then we derived motional EMF, then Lenz's law. Lenz's law is the consequence of law of conservation of energy, and then we studied eddy current and its applications. Now this is the next part of this chapter, that is induction. In that we are going to study about self-induction. Yes, self-induction is also called as inertia of electricity. So why we have to call it as inertia of electricity? That you can understand after studying about self-induction. Yes. So you can observe the first diagram. This is a circuit diagram. In this circuit diagram, we considered battery, plug key and a coil. What we are going to consider here? Consider a helical coil. This helical coil is connected to battery and plug key. Is it clear? Then, when this battery is switched on, when the plug key is closed, then current starts to flow through this helical coil. Yes, we considered a coil and this coil is having inductance L. We don't know what is inductance and L, we can study later. Just considered a coil. This coil is connected in series with a battery BA and a plug key K. When the key is closed, then the current through the coil increases from 0 to maximum. When we close the plug key, then current starts to increase from 0 to maximum value. So when a current is increasing, what are the changes occurs that you have to remember? See here, during increase in the current or during growth of the current, what happens? The magnetic flux linked with the coil also increases. See here, when a battery is switched on, plug key is closed, current is increasing and this current is moving through this helical coil. When a current is flowing through the coil, current is surrounded by magnetic field. So that magnetic field linked with the coil changes when the current increases. Here current is increasing from 0 to maximum. When current increasing, magnetic flux also increases. Right? The magnetic flux linked with the coil increases. When magnetic flux increases, as a result, EMF is induced in the coil. We already studied this concept in Faraday's law. We know that whenever magnetic flux linked with the coil changes, induced EMF takes place. Likewise, in this circuit, when the battery is switched on, when the plug key is closed, current is increasing from 0 to maximum. When the current is increasing, the surrounded magnetic flux also increases. As a result, EMF is induced in the coil. Right? Then, since this induced EMF opposes growth of the current, so this EMF is called back EMF or reverse EMF. Yes, here you have to remember Faraday's law as well as Lenz's law. We know that when induced EMF takes place in the coil, this induced EMF always opposes changing magnetic flux. Who is the cause for induced EMF? Changing magnetic flux. When induced EMF takes place, this EMF itself opposes the changing magnetic flux. It opposes growth of the current. So, this induced EMF, we are going to call it as back EMF or reverse EMF because this EMF opposes growth of the current. Is it clear? What happens here? We considered a battery, plug key and helical coil. They are connected in series. Current is increasing from 0 to maximum. Because of increasing current, because of growth of the current, induced EMF takes place. So this induced EMF opposes growth of the current. Is it clear? You can observe this second diagram here. As current is increasing, you can observe this is the direction of the current. When the current is increasing, induced EMF takes place in the opposite direction. It opposes the growth of the current. So we are going to call it as back EMF. And you can also observe the third picture. This shows the graph of current versus time. Here initially current is gone increasing during growth of the current. Means current is gone increasing, it reaches a steady rate. Means maximum value. At this point, what happens here? Induced EMF takes place. This is the time of growth. Now, in the second case, you can observe here, when this key is open, what happens when the key is open? The current go on decreases. The current through the coil falls from maximum to 0 during the decay of current, because it is decreasing from maximum to 0 here. Right? During the decay of current, again magnetic flux linked with the coil decreases. As magnetic flux decreases, as a result, EMF is induced in the coil. So this induced EMF again opposes decay of the current. So we are going to call it as forward EMF or direct EMF. Is what happens here? When the plug key is open, current go on decreases from maximum to 0 value. When the current is decreasing, magnetic flux also decreases. So when magnetic flux linked with the coil decreases, induced EMF takes place, and that induced EMF is in the forward direction. Means this induced EMF opposes decay of the current. Right? So, or you can take it as a forward EMF, or we can take it as direct EMF. In the first case, we consider making of the circuit because the key is closed, current is increasing. In the second case, breaking of the circuit because plug key is open, current is gone decreasing. In the making of a circuit, we got back EMF. In breaking of the circuit, we got forward EMF. Right? Now in the second case, you can observe the graph here. From steady current, from its maximum value to it go on decreases during decay of the current, time of decay. Is it clear? So what happens? What is the conclusion of this experiment? When current in the coil is increased, magnetic flux increases. Due to increase in magnetic flux, induced EMF takes place, and this EMF opposes growth of battery current. Then in the second case, when a current in the coil decreases using that plug key, magnetic flux decreases. Due to decrease in magnetic flux, induced EMF takes place, and hence current induces in the coil, and this induced EMF opposes decay of battery current. Then what do you mean by self-induction or inertia of electricity? You can observe the definition. The phenomenon of production of an opposing EMF. We are going to produce an EMF, but it is always in the opposite direction. So, the phenomenon of production of an opposing EMF in the coil due to change of current in the same coil. This is called self-induction. By itself, it is going to produce induced EMF. By itself, the coil is going to produce one more current, but it is always in the opposite direction. Or we can also define it as the phenomenon of induction of EMF. Yes, hence the current in the coil due to variation of current in the same coil. Yes, what is self-induction here? When a current in the coil changes, one more current is produced. Got it? When current in the coil changes, that may be increasing or decreasing. When current in the coil changes, then induced EMF takes place always in the opposite direction. So we are going to call it as a self-induction, self-induced EMF. The coil is itself going to produce one more current only by changing the current. Yes, what is self-induction? It is the phenomenon of production of opposing EMF in the coil due to change of current in the same coil, or the phenomenon of induction of EMF and hence current in the coil due to variation of current in the same coil. This is called self-induction. Yes, observe the note point here, the first point. As time of decay is less than time of growth. Time of decay is less than time of growth, so that forward EMF is greater than back EMF. Observe the picture here, you will get to know time of growth. To increase the current, it takes more time. Practically, you can observe in the laboratory. Now you can observe through this graph. Time of growth is larger. You can observe this picture. Time of growth is always greater than a time of decay. It takes more time to increase the current, but it takes less time to decrease the current. Time of growth is greater than time of decay, so that forward EMF is greater than backward EMF or back EMF. Right? Then second point, as back EMF opposes growth of current, then forward EMF opposes decay of current. So, self-induction is also known as inertia of electricity. Why we are going to call it as inertia of electricity? Because whatever the induced EMF takes place in the coil, it opposes growth of the current as well as decay of the current. It opposes movement of the charges. So that's why we are going to call it as inertia of electricity. Yes, why self-induction is also called as inertia of electricity? Because back EMF opposes growth of the current and forward EMF opposes decay of the current. So we are going to call it as inertia of electricity. Yes, now we can study about self-inductance. Till now we studied self-induction. Don't get confused. This is all about self-induction. Now we are going to derive an expression for self-inductance, or it is also called as coefficient of self-induction, or it is denoted by the letter L. L indicates self-inductance, or we can also call it as coefficient of self-inductance. Right. Now see here, I am going to consider the magnetic flux linked with the coil. See here, magnetic flux linked with the coil. It is directly proportional to current flowing through the coil. When current is flowing through the coil, current is surrounded by magnetic flux. Current increases, magnetic flux also increases. Current decreases, magnetic flux also decreases. That's why magnetic flux linked with the coil is directly proportional to current flowing through the coil, or in terms of equation we can write that is magnetic flux means generally it is denoted by pi. Pi is directly proportional to electric current flowing through the coil, that is I. Pi is directly proportional to I, or we can write it as pi equal to, we can write proportionality constant. Here proportionality constant is denoted by L into I. So what is L here? L indicates coefficient of self-induction, or this is the proportionality constant, where L is proportionality constant. L is proportionality constant, and it is called coefficient of self-induction. Coefficient of self-induction or self-inductance. Is it clear? Pi equal to L into I. Now we already studied about Faraday's law. Now I am going to consider Faraday's second law. According to Faraday's second law, what is the equation? We know that E equal to d pi divided by dt. This is according to Faraday's second law. Now observe both the equations, equation 1 and 2. Equation 1 is pi equal to Li. Equation 2 is E equal to d pi by dt. So now I am going to substitute equation 1 in equation number 2. Substitute equation 1 in equation 2. Yes, what is equation 2 here? Equation 2 is E equal to d pi by dt. D by dt keep as it is. Pi means what? L into I. Yes, now differentiate this value. L is proportionality constant. This is a constant. We cannot differentiate, take outside. Remaining is di divided by dt. L E equal to L into di by dt. But we want the expression for L, or we can write it as L equal to, this equation becomes E divided by di divided by dt. Is it clear? So this is the expression for self-inductance. What is the expression? L equal to E divided by di divided by dt. Suppose if the unit amount of current is flowing through the coil in unit time, that means if di divided by dt is equal to 1 ampere per second. 1 ampere per second substitute here. Therefore, we will get L equal to E. Self-inductance is equal to induced EMF when unit amount of current is flowing through a coil in unit time. L equal to E. Then how to define self-inductance using this equation 3. You can use this equation 3 and 4 to define self-inductance. Yes, self-inductance of a coil is numerically equal to the induced EMF in a coil when current through it changes at unit rate. Equation is L equal to E divided by di by dt. Using this equation, you can write the definition. Self-inductance of a coil is numerically equal to induced EMF in the coil, that is E. Induced EMF in the coil when current through the coil changes at unit rate. Or we can also define it as self-inductance of a coil is EMF induced in the coil due to the unit rate of change of current in the same coil. What is self-inductance? EMF induced in the coil due to unit rate of change of current in the same coil is called self-inductance, and it is denoted by L. L equal to E divided by di divided by dt. Right, then unit of self-inductance. What is the SI unit of self-inductance? Observe here. The magnitude of induced EMF in the coil due to a change in the current through it is given by, we have this equation, E equal to L into di by dt. This E equal to 1 volt. When E equal to 1 volt? When current through the coil is 1 ampere per second, then L equal to 1 Henry. So that indicates the SI unit of self-inductance is Henry. What is the SI unit of self-inductance? SI unit of self-inductance is Henry, or you can write simply capital H. Then how to define 1 Henry? Self-inductance of a coil is said to be 1 Henry if 1 volt of EMF is induced in the coil when current in it changes at the rate of 1 ampere per second. When induced EMF is 1 volt, current is 1 ampere, time interval is 1 second, then self-inductance is said to be 1 Henry. Right? So this is all about self-induction, then self-inductance and its equation with SI unit. Is it clear? So in the next class we can derive self-inductance of a solenoid.